So now let's take one example. Take one example. So now when we suppose we have the hydrogen atom, we have hydrogen atom, and this hydrogen atom is at n equal to state. Okay, and now let's neglect the spin effect. Okay, so let's neglect the spin at this moment. So now for n equals to state, so now we have the wave function that the state should be, we have 4 states, n equal to L, because n equals 2, on L could be equal to 1 and 0, right? So when L equals 1, n can equal to -1, 0, and 1, and L equals 0, my m can equals to 0. So we have 4 states with the same energy. E2 equals -2 squared, 13.9 or 13.6 eV. Right? So this is how large? 你们应该记得这数是多少？负13.6，下一个是什么？3.4吗？
对。
是吗？
对。
3.4 minus 3.4 TB. Okay, and these 4 states, we got 4 states, and L M equals 2, 1, 0, or 2, 1, 1, 2, 1, 0, 2, 1, -1, 2, 0, 0. Okay. So we have 4 states, and these 4 states have the same energy, -3.4 eV. So we got 4 folded for accuracy. Okay. And now, well, it degenerates, and now we try to break this degeneracy. So now we apply uniform or constant electric field E. Why? I don't want E is the same. Give me a notation.
用写2条线的那一种，
写2条线，
就在E旁边再多写1条线。
Eh. Can I use this? Okay. I apply a constant electric field in the z direction, and this is called the Stark effect. All right. So now we have, in addition to the usual Hamiltonian, because of this electric field, we have additional potential, right? What's the additional potential? And this additional potential, I treat that as a potential. What's that? What it is? This is E, the charge, electric charge of the electron. And then I have the electric field, and also in z direction, E epsilon z. This is my perturbation. Okay, so now let's go back to the lesson we learned in the last lecture. So the key point is that we have to find a new basis, right, which can diagonalize S1. So originally we have this 4. So let's try to find the linear combination of these 4 to diagonalize this H1. But before doing that, we can try to see the in this odd element, or in this odd basis, what this H1 looks like. So in this odd basis, H1, check the matrix of H1 in all bases. Okay, which means and L and this basis. Okay, so now let's check. H1. So we have I have 2, 1, 1. Let's see. This one 0, 0, 0, 1. I can take this 0. That's better. 2, 0, 0, 2, 1, 0. This is better. 2, 1, 1, 2, 1, minus 1. And same here. Okay, so let's check. So we got H1. We check this one first. 2, 0, 0. H1, 2, 0, 0. Over here. So this is integration wave function 2, 0, 0 or theta phi. I cannot memorize what the how this wave function look like. It must be complicated, but anyway, you can find it in the textbook, right? And then this is Hamiltonian. H1 is over here. So E Z. And I have another wave function again, theta phi, and then R squared sine theta with R with theta with phi. Okay? And then you plug in the Z. This is constant, right? Constant. And this is Z. Z equals R cosine theta. You plug that in, then you do the integration. 就把它放进去，然后做积分这样。这个把它套进去，这个是那个波函数嘛？氢原子的波函数你可以查得到。氢原子的波函数放进去积分大。It's easier said than done. 讲的比较快。Yeah, indeed, it's very quick. It's zero. Okay. Well, 我想你们忘记了 Z， 然后这 L 是0，这一定会是0的。Go back to your note in modern physics. I don't want to repeat here again. 就是我记得我在量力里面讲说，我在那个记录里面讲，这一定会是0的。Z， 然后应该有啊，应该有。Anyway, well, you do the integration, that's 0. Well, not only that, you check to all the diagonal elements to 1, 0, H1, 2, 1, 0, again 0, 2, 1, 1, H1, 2, 1, 1, 0, 2, 1, minus 1, 1, 0, a lot of zeros. And then we have, when you check 2, 0, 0, E, H1, 2, 1, 0. When you calculate that, you see this is equal to integration to 0, 0, R cosine theta, integration, and this is 2, 1, 0, and R squared sine theta, dr d theta, d phi. Okay. When you do that, well, we found that this is minus 3, not 0. E times minus 3 A naught. So this is equal to minus 3 E A naught, where A naught is I did not copy that. Anyway, A naught is something here. This for 4 radian. Okay, you just fill this one in by yourself. 所以这个 A 零是那个波尔半径，波尔半径 A 零的波尔半径，可以吗？然后你积出来之后，它就是 A 零，然后对。So finally, your H1 in this spaces looks like looks like 0 and off diagonal 3 E A dot 0 0 minus 3 E A dot 0 0 0. All the other elements are 0. Okay. So now H1, obviously this is not diagonalized. This is not diagonal matrix. So we have to diagonalize this. Well, all the other elements are 0, so it doesn't really matter, right? Therefore, which part matters? Which part matters? This part. This part matters, right? So we just diagonalize it on these two parts. So let's diagonalize. Let's diagonalize this part. And if you still remember the diagonalization we have done last lecture. Last lecture we diagonalized this matrix, right? 0 lambda lambda 0. And so when you diagonalize it, the new state, eigenstate, will be square root of 2. This guy, this one is 2, 2, 0, 0 plus square root of 2, 2, 1, 0. And also another one is square root of 2, 0, 0, 0. And with the eigenvalue minus 3e from e naught and 3e naught. Right? So which means because in this case, when we diagonalize it, it goes to lambda minus lambda, right? 0, 0. Okay, so in this case, lambda is minus 3e and not. So, well, which means on 0, a not. Diagonalize into Well, what does that mean? Which means we have the energy over here, which is minus 3.4 eV, right? And over here in this energy table, I have 4 states: 2, 1, minus 1, 2, 1, 1. And also, I have square root 2, 2, 0, 0, plus square root 2, 2, 1, 0, and square root 2, 2, 0, 0, minus square root 2, 2, 1, 0. I have 4 states in the same state, in the same energy level before the perturbation. And after I apply this perturbation, it's 1, and this is E. After I apply this perturbation, the energy split to split to here. So this is minus 3.4 eV plus 3 E epsilon A naught. Okay, so the splitting, the size of the splitting is 3 E A naught. And which state will go to here? Which state? This state. Okay, so this state will go to will raise up to 0, 0, minus square root 2 and 2, 1, 0. This state will be raised up. Another state, this state will be pulled down. Square root 2, 2, 0, 0, plus square root 2, 2, 1, 0. And split will be pushed down to minus 3 epsilon A naught. Okay, the same splitting, but split down. And there are still 2 states remain unchanged. Which 2? These 2 states remain unchanged. Okay, so these 2 states stay here. 2, 1, minus 1, 2, 1, 1. So this perturbation doesn't break the whole degeneracy. It just breaks down these 2 degenerate states. We still have 2 degeneracy over here, 2 false degeneracy over here. Is that okay? Good? Okay. Well, so up to now, probably I don't know, you should have a sense that how to deal with this perturbation. this perturbation. So, for example, over here, we use the odd basis, which is not the good basis. We use this basis, odd basis, to write down the matrix form of the perturbation, right? And then do the diagonalization of this perturbation. When you do that, you will find out the new good basis, which are the linear combination of the odd bases. Is that clear? That's a standard step procedure in order to do with the perturbation of the degenerate case. 所以你们刚刚有一个例子，那刚刚只是一个简单的一个toy model， 一个给你一个简单的2×2的矩阵，要告诉你怎么做，对吧？那这边呢是实际上的一个状况，实际上的状况，一个氢原子加了它在这个n 等于2的这个 state 的时候呢，它是简并的，那我就加了一个电场之后呢，它的简并呢就会被打开，这个简并就会被破坏，是吧？但是比较遗憾是在这个状况之下，其实还有2个 state 它是还是简并的状况，但没有关系，我的目的就是要告诉你说，在这个状况呢，实际上这物理系统呢，我们要怎么做？你看，这是 perturbation 的这个 matrix 的样子，那它很明显它是没有对角化，所以当你写下来之后，你就把它对角化。当你对角化这个 H1 的时候呢，那 perturbation 的时候，你自然而然就找到什么？就找到一个好的一个 basis， 这样可以吗？这个是不好的 basis， 原来的这个 LML， 原来的这个 LN， 这个是不好的 basis。OK， 那当你做 diagonalization 的时候，你自然而然就可以找到一个什么东西，找到一个好的 basis。OK。Okay. So if you think that, well, it may be difficult or very ambiguous to find the good basis, so-called good basis, and then there's a way, another way you can find it. So far, we just directly diagonalize the H1, but there's another way. Another way to find out good basis. The diagonal. Assume. So now assume. Let's assume. Assume we have another operator. Operator omega. Okay. Lambda. Let's say lambda. I have another operator lambda, and lambda and H1, the perturbation commute. Okay. So assuming you have another operator, I don't know which one, but anyway, you have one, and I call it lambda. An interesting thing is that if it's a lambda and H1 commute, and the eigenvalue lambda 1, lambda 2, lambda k are eigenstates of lambda and with eigenvalue lambda 1, lambda 2, lambda k, where lambda 1, now lambda 2, lambda 3, lambda k, which is not degenerate. So if you find the states with this which are not degenerate in this lambda and now the operator lambda, and then this lambda 1, lambda k are from good basis in which where H1 is diagonal. So if you have another operator lambda, then you know everything. You know the eigenvalue, eigenstate, and this not degenerate. This and this lambda H1 commute. Therefore, you already find a good basis. I guarantee you that this eigenstate of lambda will diagonalize with H1. Okay, and the proof is also very easy. Because lambda H1 equals 0, because this is 0. Okay, so then I sandwich this by two states, lambda I lambda z, because this is 0, and no matter how you sandwich this, it also equals 0, right? Is it obvious? Okay. 因为他们两个是共论嘛，那叫共论。commute叫做什么？对啊，所以你们也不知道中文啊，对不对？对义吗？对义是什么东西啊？Anyway, commute OK 吗 ？commute。OK， 因为他们两个这 commute， 所以我现在把这两个这个零呢，用两个 step 把它加起来。那把它加起来之后，它还是零嘛，对吧？没问题吧 ？OK, so this is obvious 0, and now next step, let's expand it. Okay. So let's expand it my this equation. Well, so let me expand it. So now I got lambda I lambda hi minus h1 lambda z equals 0. Okay. Yeah, I forgot to write this. This is having a condition. Okay. So I have lambda I see, minus zero. So you can see that here equals okay lambda I don't need to write. I mean, this means lambda I equals lambda I, right? I don't need to write that because that's eigenstate, the definition of eigenstate, eigenvalue, isn't it? So now this part equals lambda I, okay, and lambda I do this. H1 lambda Z. And the second part equals lambda I H1, but this part equals lambda Z equals 0. And then you combine together lambda I minus lambda Z times lambda I H1 lambda Z equals 0. Okay, so if lambda I not equal to lambda Z, which they are different states. If they are different states, this is non-zero, right? So if this is non-zero, by the times this guy equals 0, which means this guy equals 0. Okay, if so. It must be equal to 0. Okay. So what does it mean? What does it mean? This is the matrix form. This is matrix element. H1 I Z, right? And I is not equal to Z. So, I not equal to Z. So this is the matrix form in this basis. This is H1 matrix form for the H1 in lambda I lambda Z basis. 这是 H 的这个矩阵形式，对不对？在这个基底下面所展开的那个矩阵形式嘛。那 I 不等于 J 的时候呢，它就要必须等于0，也就是说呢，这个matrix element 呢，这个 I J 要等于0，但是 I 不等于 J， 意思就是什么呢？意思就是 off diagonal， 可以吗 ？I 不等于 J 就是非对角线的那些元素嘛，是吧？ Is that okay? So I not equal to J, and this element vanished, which means all of the off diagonal element vanished, which means that lambda this space is diagonalized. So now. All right, any question? Now about the homework, last week I totally forgot when I refreshed my brain, and it's already Monday, so I think it's too short for you to do the homework. So I decided to combine the last homework and the homework this week together. Okay. Well, don't worry. Don't worry. So yeah, so certainly this week we will have homework, right? And yeah, still I got roughly 5 minutes. But it won't be enough to do the next topic. So any questions? 我剩下不到5分钟，我当然没有时间再讲下一个，那就下一个就留到下个礼拜 ，OK， 好，所以下个礼拜我们就把这个 degenerate case 把它结束掉，然后再做下个 topics，OK， 那今年的进度看起来还不错，去年的进度可能那个 degenerate case 就是举一个例子就结束了，好像是这样。今年可能还可以讲到 time dependence， 甚至可以讲到 variation， 就是另外一个 approximation method。OK， good。有什么问题吗 ？Any questions？ 好啊，那如果没有问题的话，就今天就到这边。哦。
我不喜欢挺大的。没有，那个老板还行啊。但是觉得他东西挺贵啊，还有他东西真的挺贵。感觉。我跟你讲，他最近挺高的。我们年前最近晚上。
See you guys.